AC through an inductor. That is what the topic will start with. So the topic is AC alternating current, AC through an inductor. So what is actually an inductor? Inductor is actually a helical coil of metal wire. That's it. That's what you can think of. Okay. So it's called, you have, what you have is, it's like a helical coil. What you have, metal helical coil, and it has something called a property called inductance. It has a property called inductance. It is measured, it is represented as L, and it is measured in Henry. Actually, the units are Henry. The units are Henry. And suppose this inductor coil is connected to an AC source. We'll assume that it is connected to an AC source. If it is connected to an AC source, we'll represent like this. One symbol we'll put like this. And this is what is an AC source. AC source is represented. We'll put a circle like this and then put a symbol like this. That means it's an AC source. Okay. Hope you got this concept. And now that AC will have an EMF of E is equal to E naught sine omega t. So this is what happens for an AC source. So we have there is something called a Lenz law. In that we have seen the EMF what is generated from the Lenz law is given by minus L into di by dt. This is from, the equation is from the electromagnetic induction, where rate of change in the current minus L into di by dt. That's what the EMF is. Okay, ma? And E is the induced EMF. This is actually induced EMF. Induced EMF. Induced EMF is given by this equation minus L into di by dt. Now, so when the AC is going, the moving along the circuit, okay, we assume that there is a tap key over here. When the key is closed, so we can write a statement, when the key is closed, the current I begins to grow. So up to this point, you can please write. Later we'll do. I begins to grow. Now, as we read in the moving charges and magnetism, if there is a wire and the current flows through that, there is a magnetic field generated about this conductor radially. This we have discussed. Okay, there is a moving charge that is associated with the magnetism exactly in the radial direction. So when you have an alternating current, the magnetic field also becomes flip-flop. Means like in one moment the current will be this direction, the other second the current will be in opposite direction. So the magnetic field will be also changing because of this current. Hope you know this, right? Can I clear this?
Yes, sir.
Yeah. The next one. Now, the idea is that when the current I begins to grow, because magnetic flux, because magnetic flux linked with it changes and induced EMF produces which opposes the applied EMF, which opposes the applied EMF. So the magnetic field, the variation in the magnetic field will generate the induced EMF. This is the Lenz law. So we write the induced EMF, epsilon is given by minus L into di by dt. This is the di by dt refers to rate of change in current, rate of change in current. So that is what di by dt is. Can I clear this? Hope I can clear. Now, to maintain the flow of current in the circuit, to maintain the flow of current in the circuit, applied voltage must be equal and opposite to the induced EMF. Now, based on this logic, E is equal to minus E, you can write, that is the epsilon, minus of epsilon, that is minus L into di by dt. Just a minute. Yeah, good evening, madam. Tomorrow evening, madam. Tomorrow 8:45. Yeah, okay, madam. Tomorrow 8:45 to 9:45 is okay, madam. The time is fine. No problem, madam. And Saturday morning is also fine. Okay, madam. Okay, madam. Okay. No problem. Yes, madam. No issues. No issues. 8:45. Yeah, that is also fine. Saturday evening, fine. No problem. Anytime. Saturday evening after. Yeah, yeah, yes, madam. Saturday 7:30 to 8:30 is also fine, madam. No issue. We can plan. Okay, madam. Okay, madam. Okay, madam. Yes, madam. Yes, madam. Okay, madam. You please send me the link, madam. 8, we can have 8:45 to 9:45. No problem, madam. Okay, madam. Okay, madam. Okay, madam. Oh, okay, madam. Okay, Sunday. Sunday. Okay, that Sunday I will maybe, madam. That Sunday I will postpone or something. I will do. No problem. That one day I will adjust. No issues. So, oh, okay, madam. That Sunday maybe afternoon we can plan. No problem. I'll come in the afternoon then. No problem. Okay, madam. Okay, madam. Okay, madam. Okay, madam. Right, madam. Okay, madam. Right. No problem. No problem, madam. I know that, madam. No problem. Okay, madam. Okay. Hello. Yeah. Hopefully you had have written this. Now what minus of minus is plus? You can write L into di by dt. You can write this. Just a minute. Hello. Yeah. So we have L into di by dt. Or you can write di. Let's write for the current di. So the current will be E by L times dt. But E, we know that E is equal to E naught sine omega t. So we'll substitute E naught sine omega t. Okay, dt whole divided by L. So written this.
Yes, sir.
Okay. Now the idea is to find the current. So the current di is equal to, I have E naught by L. Okay. E naught by L sine omega t dt. Let's write like this, sine omega t dt. Now let's integrate on either side. The current rises from 0 to I, and then we integrate. E naught by L is a constant, so we'll integrate 0 to T. So when I give the integration, I'll get a result over here, that is E naught, negative E naught by omega L cosine of omega T. This is what I get. Just a minute. Hello.
Yes, sir.
Yeah. So this one you understood. So the integral sine omega t is negative cos omega t divided by omega. That's how we get. And then when you substitute, this is what you get. And now the idea is to find the phase difference between. So I got the current. This is the most important thing. Current, I got the negative direction of this one. You see, minus E naught by omega L cosine of omega t. Okay. Now this is what I got. Uh, so now how to express this? How to find the phase difference? So we'll write negative of E naught by omega L. We can write sine of. I always told you that you have to write the pi by 2 plus omega t. You can have pi by 2 minus omega t also gives the same answer, but pi by 2 plus omega t you take. And the phase difference is about pi by 2. So you can have the phase difference. So the phase difference, let's work out. So the negative value will take inside. So if I consider the negative inside, I'll take the negative inside. So let's equate this. I is equal to minus E naught by omega L. If I take the negative value, sorry, if I take the negative value inside, sine of, it becomes minus pi by 2 minus omega t. This is what I get. Okay, let's put it like this. Let's put it in this way. So you can write, I hope you have written. So here the phase difference, this is what you have to remember. Phase difference between the current and the phase difference between the current and voltage is pi by 2. So that will be 90 degrees, the first part. Second part of it. Second part is that I told you to remember Li, the Iceman. The Li stands for voltage E means voltage. Voltage E leads the current I. So voltage comes first and then I comes next. Okay. Voltage leads current by pi by 2. The L stands for inductor, for an inductor. This is how one can remember. The overall phase difference is pi by 2. You can take the positive value, so it is pi by 2. But the Li, the Iceman, if you remember, so it is voltage leads the current by pi by 2. This is how one can remember. So the other way of representing the current is like this also, I naught sine of omega t minus pi by 2. This is the other way of representing the same current. In this case also, you get negative I naught cosine omega t. So here I naught refers to E naught divided by omega L. I'll tell you what is this part. So in the case of resistor, I got I naught is equal to E naught by R. This is how we have taken in the case of resistor. But in the case of inductor, I naught is E naught by omega L. So what is this omega L? It does the play of the resistance. It does the play of the resistance. It does the play of the resistance. Lock this. It does the play of resistor. So that omega L part, we will call this is called XL, which is called inductive reactance. Inductive reactance, which is called XL, that is equal to omega L. So it is dependent on the frequency. XL is equal to omega. Omega is equal to 2 pi f. So we will write 2 pi f L. So that is called inductive reactance. And now you have the phasor diagram. How the phasor diagram looks like is, I said the voltage leads the current. The phasor diagram wise, we will draw the E naught, the vector. This length is E naught. And the current will be shorter than that of E naught. This is what we draw. Ensure that this angle between them is pi by 2. That is 90 degrees. With that, the phasor diagram is also complete. So this is the E. This part is the E. And this part is the I. E and I. So if I draw this, voltage leads the current. So this is how it looks like. Voltage on the top and the current will be at the bottom. Current will be, the vector will be rotating like this. Remember, the vector rotation is anti-clockwise. So the voltage rotates faster, and whatever the position voltage has already got, the current will get that later. So that is what the lead is. Now I'll tell something about inductive reactance. Inductive reactance. The opposing nature of inductor of inductor to the flow of alternating current, to the flow of alternating current, to the flow of alternating current is called inductive reactance, is called inductive reactance, is called inductive reactance. So I have given the equation. XL is omega L or 2 pi FL, which is called inductive reactance. And the units of inductive reactance is ohms, ohms only. Inductive reactance has a units of ohms. So there is one important point for DC source. For a DC source, omega is 0 for a DC source. So inductive reactance for DC is 0. Very important for DC. For DC, inductive reactance is 0. So let us solve a problem. They have given the EMF E is a problem. EMF E is given by 220 sine 100 pi t. 220 sine 100 pi t, like this it is given, is applied to the circuit containing inductance of 1 by pi Henry. it is applied to the circuit of 1 by pi Henry. Write the equation for instantaneous current through the circuit. What will be the reading of the AC? So we have this one which is given. So from this we can find what is E naught. E naught is 220 volts, and omega is 100 pi. Omega is 100 pi radians per second. That's the units of omega. L is 1 by pi Henry. And inductive reactance is what they ask. XL is equal to omega times L. So omega is 100 pi times L. L is 1 by pi. Right. It will be 100 ohms. So this is how one can calculate. That's what you get is 100 ohms. And the inductance is measured in Henry, H for Henry. And I naught one can calculate, that is E naught by XL. E naught is 220. The XL we got 100. So it happens to be 2.2 amps. That will be the current. The instantaneous current equation, I is equal to I naught sine omega t. Omega t is 100 pi t minus pi by 2, as current lags the voltage. As current lags the voltage, or voltage leads the current, or current lags the voltage. Both the things you can give. Both the things you can give the answer. These are the things what I can tell you today. And so the next one is that IRMS, this is what they asked. IRMS, that is I naught by root 2. So the I naught value is, I naught value we got, that is 2.2 amps divided by root 2. And that is 2.2 by root 2. That's where we left amps. 1 by root 2 value you can substitute and get it. And now whatever the RMS value you see, this will be the reading. This will be the reading you see on an instrument. You see on an instrument. So this much is sufficient today. So tomorrow we'll see AC through a capacitor, and then phasor diagram, and few more things are there. With that, this AC circuits can be finished. Yeah, please note it. So this is sufficient today. Tomorrow we'll meet at maybe the 7:15, like that we'll meet tomorrow. Yeah, thank you all. After writing this, you can leave, no problem.
Thank you, sir.